All right, let's look now at section 9.3. Let's talk about the integral test and the p-series. So we begin this section with a theorem. Let f of x be a function that is positive. And every time you plug in something into f, you get a positive number. It's continuous, and it's decreasing. The values go down as x goes up. For every value of x that's greater than or equal to 1. If this is satisfied for x is less than 1, that's fine. And if it's not, that's okay too. We just care about it from x is greater than or equal to 1. Now, let the sequence a sub n be a sequence where the nth term is given by f of n. So you want the first term of the sequence, plug in 1 into your function. You want the 10th term of your sequence, plug in 10 into your function. So here, the series, as n goes from 1 to infinity of a sub n, and the integral from 1 to infinity of f of x with respect to x, either both of those are going to converge, they're both going to give you an answer, or they're both going to diverge. Note, it doesn't say that the answers are the same. It just says if one converges, so does the other. If one diverges, so does the other. If this converges to 12, this might converge to 4 million, or vice versa. So it doesn't say anything about what they converge to. This just says either both will converge or both will diverge. The proof of this is best motivated through an illustration. So let's consider a graph here. And we're going to go ahead and bound the area given by the graph a couple of different ways. All right, so consider a function that is positive, that is continuous, and that is decreasing for all values of x greater than or equal to 1. So starting from 1, it's going down this way. Okay, and here I'm going to do the same thing for, I'm going to just draw the same graph over here. These are meant to be the same graph, but I'm going to go ahead and illustrate the two graphs with different boundaries. Okay. So now imagine that you're looking for the integral from 1 to infinity of this function. Okay, well then by what we've seen in chapter 8, one way you could interpret that is we're looking for the area underneath this curve starting from 1 all the way out to, well, forever. There is no end to that. And same thing over here. You're looking for the area starting from 1, and it just sort of goes on that way. Okay? So the reason I've drawn this graph two different ways, or two different times, is not because they're a different function. Here I intend for this to be f of x both times, the exact same function, but rather because I'm going to bound it using a set of rectangles. And the way I'm going to bound it is, first, consider what happens if I bound it from below. So consider these rectangles that are all underneath my graph. Okay, so that's 1, and that's 2, and that's 3. Here, I'm not going to make these infinitely thin. I'm just going to keep them all width of 1. So 1, 1, 1. And it would keep going like that until eventually you'd reach n minus 1, and this would be n. Notice these are just subsequent integers. All right, n minus 1, and then the next one would be n. All right. So here, this is sort of like the graphical version of dot, dot, dot. Here we have some stuff which we're not worried about right now. They're there. We're just not going to draw them. Okay. Now, imagine that you're bounding this with these rectangles. Well, then that means that the sum of the area of these rectangles is less than the area underneath my curve. Okay. Now I'm going to do the same thing over here, except that instead of bounding it from below, I'm going to bound it from above. And I'm going to do the same thing. I'm going to keep my rectangles to be a width of 1. But now, instead of having them be too small and all rest underneath my curve, now I'm going to have them all be too big and rest on the outside of my curve. Notice here, instead of starting from the right endpoint, here I'm starting from the left endpoint. And the left endpoint gives me the height. Since the function is decreasing, that guarantees that my function will always be just a little outside of my curve. And again, we'd have these kind of rectangles going on and on until eventually we reach something like n minus 1 and n. Okay, so visualize, or rather, notice the visuals given here. Well, notice the sum of these rectangles, here the sum of the area of the rectangles is given by, well, it depends on which one we're looking at here. This one is given by, notice here, my function, I'm always taking the left endpoint. So this would be f of 2, f of 3, f of 4, f of 5. Now remember, the bases are always 1. So here, the sum of the area of the rectangles is given by base times height. Okay, so that's going to be f of 2 times 1 plus f of 3 times 1 plus f of 4 times 1, and so forth and so on. Notice times 1 doesn't change anything. So here you could just write this as the sum of f2 and f3 and f4 and so on. Using summation notation, we could write that this way. We could say that's the sum as n goes from 2 to infinity. Notice we're starting from the number 2 of f of n, like that. Oh, but here we don't want this to go to infinity, at least not yet, because if it goes to infinity, there's going to be some stuff that we can't manipulate. So here, let's go ahead and say, okay, yeah, I know this will eventually go to infinity, but for now, let me go ahead and stop at some point. Now, I noticed that, well, I've already used n here. So here, I don't want to say n goes from 2 to n. That would be redundant, right? That would be, I shouldn't use the same symbol twice. So here, instead of n, I'm going to use a different notation. Up to now, we've been using n is equal to something. But here, notice that n is the number of these rectangles that I have. So here, I'm going to say, okay, instead of using n for which rectangle I'm at, I'll use n for the total number of rectangles. So here, I need a different letter. Some books use I, some use J, some use K. This book, I believe, uses I, so I'll go ahead and use that same letter. That's not the imaginary number or anything like that. It's just, you know, instead of N or X, they use I. Okay. Now, here, this is going to go up to, well, this one started at 2 on the right side, and then 3, and then 4. The very last one is going to start at N, so that's going to go from 2 up to N. All right, so this is the sum of the area of these n rectangles. All right, now I can do the same thing for this one. And the sum of the area of the rectangles, well, that's going to be, notice here I'm starting from the right. So that's f of 1 times 1. And then this one's f of 2 times 1. And f of 3 times 1, and f of 4, and so forth. Notice that the very last one, notice I'm starting on the left-hand side of each rectangle. Here, the left-hand side of this one is n minus 1. So the very last one I would eventually get to would be f of n minus 1 times 1. Now, of course, here, these times 1s don't change anything. So really, this is just f of 1 plus f of 2 all the way up to f of n minus 1. So I could write that as the sum as I goes from, now here I'm starting at 1, as opposed to over here where I was starting at 2, from 1 up to, and this isn't going all the way to n, it's only going to n minus 1, the left-hand side of each rectangle, of f of I, like this. So here I can represent the sum of the area of these two rectangles, or rather, these two sets of rectangles. All right, well now consider the area that they're modeling. Here I want the area from 1 to infinity. Yeah, but again, that's nonsense. We're going to take the area from 1 to n and then let n approach infinity. So here, if we're approximating the area using these rectangles, notice this area is not enough and this area is too much. So we could write that as the area from 1 up to n of f of x dx, or in other words, the area underneath the curve. We know it's got to be more than the sum of these rectangles because those are all too small. And we know it has to be less than the area of these rectangles because these are all too big. Just like that. But notice, this is just a partial sum. In fact, it's the partial sum from 1 up to, my apologies, this should have been an n minus 1. I copied that down incorrectly. So here, this is the partial sum. This is the sum of the terms starting from 1 up to n minus 1. Oh, that's the n minus 1 partial sum. The sum of the first n minus 1 terms. Now, this is the sum of the first n terms from 1 up to n. And you say, that's not 1. Oh, okay, right. So this would be the nth partial sum, except that first term is missing. Oh, well, you know what? This is the nth partial sum if I just subtract away f of 1. Here, I don't have I equals to 1. It's not there. Okay, so then I should subtract it away from the full sum. This would be from 1 to n. Well, I really want from 2 to n. Okay, so subtract away that very first one. Just like this. But now, note that this, if we let n approach infinity, is going to give us the integral from 1 to infinity. But if we're letting this pass through the limit, we have to let everything else pass through the limit. Well, what happens next depends on what happens to this. Let's assume, so we're going to break this into two cases. Case number 1. Go ahead and assume that the limit as n approaches infinity of the integral from 1 to n of f of x dx converges. Or in other words, you were able to find the limit from 1 to infinity. You were able to find the integral from 1 to infinity. And here, let's just, for the sake of notation, let's say it converges to a number L. Okay, well, if that converges, that means that if I look at this right-hand side, that means that my s sub n minus f of 1, my s sub n minus my f of 1, this I know will converge to L. But this is always less than or equal to this. So no matter what, this must be less than L. All right? This is always less than this. So this is eventually going to become L as n approaches infinity. Well, this always has to be less than this. So if this eventually becomes L, well, this has to be less than L. Oh, but let me go ahead and add that over to the other side here. So that means that S sub n is less than or equal to L minus f of 1. Okay, so what? Well, then that means that the sequence of partial sums, the sequence of S sub n's is, well, notice it's monotonic, because here what you're doing is you're adding up these rectangles. Every time you add another rectangle, it's growing a little bit more and a little bit more and a little bit more. Okay, so it's monotonically increasing. So here the sequence is monotonically increase. Monotonic. And here I'll write increasing, although that part doesn't really matter. All that matters is that it's monotonic. Now notice that this set of terms Sn is also bounded. After all, Sn, the nth partial sum, we know has to be less than this. Well, that's a number and that's a number, so it must be bounded by a particular number. We don't know what L and f of n, we don't know what L and f of 1 are, but we know their numbers. And since this function is strictly positive, well, then that means that all of these are positive heights. So if I add those together, they must be positive. Positive plus a positive plus a positive is a positive, which means this is bounded below by 0. Oh, so it's bounded above and it's bounded below. So that means that the terms Sn so the sequence Sn is bounded. All right? If the terms are stuck between here and here, that means the sequence of terms must be bounded. Oh, but from a previous section, we saw that if a function is monotonic and bounded, it must converge. So the sequence of S sub n's converges. But by definition, if the sequence of partial sums converges, that means that the sum converges. So by definition, after all, that's the definition of what it means for a series to converge. So by definition, we know that the sum as I goes from 1 to infinity of a sub n converges. Okay, so that proves case number 1. If the integral converges, then the sum converges. That was one of the things that our theorem tells us. If one of them converges, so does the other one. Okay, but what if one of them diverges? Maybe it's possible for one to diverge and the other one to converge. No, it turns out that won't be possible. And here's the second part of our proof. And this direction is a bit simpler. We're going to be using the right-hand side of this inequality. Here, we use this one already to show that if this one converges, so does that one. Here, we'll use this other side, which is saying the integral of 1 to n of f of x dx is less than or equal to s sub n minus 1. So case number 2. Since we know that the integral from 1 to n of f of x dx is less than or equal to the nth minus first partial sum from 1 up to n minus 1, if we assume that the integral from 1 up to infinity of f of x dx diverges, then that means that the limit as n approaches infinity of integral from 1 to n of f of x dx goes to infinity. That's what it means for an infinite, this is what it means for this form of indefinite integral to diverge. It means it's infinite in size. You say, well, how do you know it's not negative infinity? Because, of course, these are all positive terms, right? F of x was strictly positive. So here it must go to infinity, not minus infinity, since f is positive. From 1 up to whatever number you need. Okay, but if that's the case, if this limit is undefined, then that suggests that the limit as n approaches infinity of the integral from 1 to n of f of x dx, which is less than s sub n minus 1, all right, if this is always true, then it'll be true no matter what n is, all right? Limit as n approaches infinity. Then, if this is going to be infinite, this means that this value is going to be greater than or equal to something that's infinite. So that means the limit as n approaches infinity of s sub n minus 1 is greater than something that's already infinite. Or maybe it's equal to something that's already infinite. Either way, that means this can't be a finite number. So that means that the limit as n approaches infinity of s sub n diverges. That's what it means to diverge. Or that's one thing it can mean to diverge, to go off to infinity. Oh, but if that diverges, remember, this is the nth term of the partial sums, of the sequence of partial sums. So, by definition, that means that the sum as I goes from 1 up to infinity of a of n diverges. So this concludes that if we assume this integral diverges, then so does this infinite sum. All right, and that proves the other part. All right, the first part proves if one converges, so does the other. The second part concludes if one diverges, so does the other. So consider the example. Here, let's start off on a new page here. Let's consider an example. And here the question is simple. Does the series converge or diverge? Does the series converge? Now, this is going to be a common question throughout this chapter. This sounds like a yes or no question, and it really is, but there's more to it than that. You can't just say yes, it converges, or no, it doesn't. What we have to do is we have to confirm that it's true or not. This is not a 50-50 guess. So whenever the question is, does a series converge, part of your answer will be either the word yes or the word no. But the other part, in fact, the main part of your answer will be, okay, and here's why. Usually, the way it'll work is you'll say, yes, it converges, and then you'll have a reason because of the integral test, or because of the p-series test, or because of the geometric series test, or whatever. And then after that, you'll say the results of the test. So here, this will be one of the first examples we see of this. We saw a couple in the previous section, but in those sections, we had an actual numerical value. We said, oh, the series converges to this number. Many times, we won't be able to get a definitive number. So this would be what most of our answers look like. So consider the series, the sum as n goes from 2 to infinity of the quotient 1 over n square root of the natural log of n. Okay. First of all, you might say, well, look, that's n goes from 2 to infinity. Isn't it supposed to be 1 to infinity? That's fine. The integral test is a bit flexible because remember, the integral test will test what happens from 1 to infinity. But if you start from 2 to infinity, that just means the first term got cut off. If something was finite and you cut off one term, it's still finite. If something was infinite and you cut off a single term, that's still infinite. If you have an infinite amount of stuff and you take one away, you still have an infinite amount of stuff. So here, even if it doesn't start at 1, as long as it starts at a finite value and goes to infinity, you can still use the integral test without any problem. You don't even need to modify anything. You just need to take the integral. So for this one, we recognize, hey, look, 1 over n square root of natural log of n. If these were x's, this looks just like one of the u substitution property, or one of the u substitution problems that we have in chapter 5. So here, let's take a look at the integral. Consider the integral from 2 to infinity of 1 over x square root of the natural log of x dx. Right? So we're going to consider the integral version of this. Okay, so now, remember, this is nonsensical. This really means the limit as the upper bound, which we call b, goes to infinity, of the integral from 2 to b of 1 over x square root of the natural log of x dx. And that is something we can evaluate. Here we can use the fundamental theorem to find an antiderivative, plug in the endpoints, and then we'll take our limit. And it should be in that order, right? So let's go ahead and find an antiderivative of this. Here, I'm not going to worry about boundaries here for just a second. This is just a bit of side work. I'm going to take the antiderivative of 1 over x square root of the natural log of x dx. Here, let me take that as my u. So let's say u is equal to the natural log of x, which means du is equal to 1 over x dx, which means this can be written as the integral 1 over x dx. 1 over x dx, that's just your du, over square root of the natural log of x. Well, that's a square root with this inside, so it's the square root of u. Okay. We can write that as the integral of u to the minus 1/2 du. And now things are nice because I'm allowed to use the power rule now. I can write this as, if I add 1 to the power, that's going to give me u to the positive 1/2. And then I'm going to divide by positive 1/2 plus a constant of integration. And of course here that's dividing by 1/2 is the same as multiplying by 2. So this is a little bit of side work, and it shows me how I can find my antiderivative of this. So now we take the antiderivative and evaluate at the endpoints. So this is going to be equal to the limit. I'm just considering down here, this is just some side work. This is going to equal to the limit as b approaches infinity of 2. I almost forgot here. My u, I'm going to go ahead and plug the natural log of x back in. So that'll really be 2 times the square root of the natural log of x plus a constant of integration. So here, that's going to be my antiderivative. So now I can take that antiderivative, just like that, and I can go ahead and plug in these boundaries from 2 up to b. All right? Of course, the way that works is we're just going to write this as the limit as b approaches infinity. The b goes first, so that's 2 square root of the natural log of b minus 2 square root of the natural log of 2. Just plugging in b first, then 2, and then subtracting. Okay. Now here we're going to evaluate a limit. Note here that this is just a constant number. All right, 2 minus the natural log of 2, that's constant. As b approaches infinity, nothing about it will change. So everything will depend on this one. Okay, so let's see here. This is just a constant. Well, now here I'm taking the limit as b approaches infinity. Well, as b approaches infinity, the natural log of b will approach infinity. And if you're taking the square root of an infinitely sized number, well, that's also going to go off to infinity. All right, so here, this is going to go off to infinity. So here you have something that's infinite in size minus a constant. All right, here's infinity minus a constant. That is nowhere near formal notation, but it's a good way to get the intuition needed to express that limit as b approaches infinity. We find that this whole thing will diverge. So this is going to diverge. Oh, but now by the integral test, we know that if this limit diverges, we know that this limit will diverge as n approaches infinity, all right, as this upper bound approaches infinity. So the full answer to this kind of a question would not be just yes or no, but this would say no. All right. The series diverges by the integral test. And you say, oh, that's the full answer? Well, no, this is the full answer. Because there's 3 parts to your answer. The first part is either yes or no. Either yes, the series converges, or no, the series diverges. The second part of the answer is, okay, which test did you use? For now, we've only seen really 3 tests. The geometric series test is the one that's, well, is it a geometric series? The nth term test, which we saw in the previous section, and now the integral test. In later sections, we'll see more tests. So either yes or no. In this case, no, the series diverges because of this test. And then the third part of your answer is, well, here's what the test looks like. Okay, there we go. So this would be the full answer. Now, note that there are a couple of restrictions on use of this test. The first one's a practical one. In order to use this test, you need to be able to take this integral. You need to be able to figure out whether or not this converges or diverges, which means you actually need to be able to do this. And since part of doing this is taking an antiderivative, one restriction is, well, some functions I just don't know how to take the antiderivative of. Or if I do, it's not at all nice. But aside from that more practical limitation, there are some theoretical limitations as well. Remember, the p-series, I'm jumping ahead of myself. The test requires that your function be positive, continuous, and decreasing for all values of x which are greater than or equal to 1. Which means if any of these 3 conditions are violated, that means the test does not apply. So note, consider the series given by the sum as, let's say n goes from 1 to infinity of 5 plus the cosine of n over n squared. Something like this. This would not be a candidate for the integral test. Why not? Well, let's see. Anytime I plug in a number that is greater than 1, here this would be a positive number. Cosine might be positive or negative, but we know it's got to be between -1 and 1. And if we add 5 to a number between -1 and 1, we're going to get a positive number. Okay, so a positive number over a positive number. Okay, that's fine. My function is positive. Okay, no big deal there. Continuous. Well, cosine is continuous, and polynomials are continuous and squared. And if you take something that's continuous over something else that's continuous, that would be continuous as well. So the continuous function 5 plus cosine of x over x squared, yeah, that would be fine. So my function is positive and it's continuous. And it's decreasing. Oh, wait, no, it's not. Because if n is a number from 1 to infinity, well, notice that cosine is a periodic function. It oscillates up and down and up and down. So here, if I have 5 plus the cosine of n, or 5 plus the cosine of n of 1 or 2 or 3, this can go up or down or up or down. So here, we cannot use the integral test on this series because it is not decreasing. At least not for every number between 1 and infinity. For all numbers n that are greater than 1. It oscillates. It goes up and down. So be mindful of that. The integral test has 2 limitations. One is practical. If you can't take the integral, well, then that's just not going to work. You'll know these behave the same way, but you won't know how this one behaves. The other consideration is, remember, you have 3 conditions. In order for the integral test to work, you must have a function that is positive, continuous, and decreasing for all values that are greater than or equal to 1. So now that brings us to what we call the p-series. Let's recall back from chapter 8, there was a result that we got in, I believe, section 8.8. Recall from section 8.8. It was one of the very last things we see in that section, and that was the integral from 1 to infinity of 1 over x to the power p dx. This will converge if p is greater than 1, and it'll diverge if p is less than or equal to 1. If it diverges, well, then it diverges. No big deal. This diverges whenever p is less than or equal to 1. But if it converges, not only do we know that it converges, we know what it converges to. We computed that as being 1 over p minus 1 whenever p is greater than 1. Okay? All right, so now this leads us to a theorem. Which states the following. Let the sum as I goes from 1 up to infinity of 1 over n to the p be a series. Here we have a name for this. This is called a p-series for obvious reasons. And it's got a variable here, which we're going to call p. So this is called the p-series. The p-series converges for all p greater than 1. And it diverges for all p less than or equal to 1. The proof of this comes directly from this result. by the integral test, since the integral from 1 to infinity of 1 over x to the p dx diverges for p less than or equal to 1, then the sum as I goes from 1 to infinity of 1 over n to the p also diverges for p less than or equal to 1. And since the integral from 1 to infinity of 1 over x to the p dx converges for p greater than 1, then the sum as I goes from 1 up to infinity of 1 over n to the p, sorry, these should all be n's. Here, this n should match that n. I've started mixing my variables here. The sum as n goes from 1 to infinity of 1 over n to the p also converges for p greater than 1. Now, unfortunately, we can't say that it converges to that, because remember, the integral test tells us that if the integral converges, the related series converges. It doesn't say that they converge to the same thing. So here, all we can say is that it would converge for p greater than 1. It doesn't say what it converges to. The p series is a very useful kind of series to be able to handle, because many of the series that we see throughout this chapter will either be a p series or will be related to a p series. If they're related to a p series, there's still a little bit more work to do, which we'll see in coming sections. But if it is a p series, then we're pretty much done. So for example, a question might read, again, does the series converge? And here we're given a series, and let's have one that's not explicitly given in summation notation. Let's have one that's given out by the sum of its first several terms. So here, this is the series 1 plus 1 over the cube root of 4 plus 1 over the cube root of 9 plus 1 over the cube root of 16 plus 1 over the cube root of 25 plus dot, dot, dot. Here, you could think of that 1 as being 1 over the cube root of 1. And that'll help establish the pattern even further. Notice the numerator is exactly 1. The denominator is the cube root of the squares of 1, 2, 3, 4, 5, and so forth. It may be useful to write this using this summation notation. Going back to what we saw in a previous section, if you have one of the few established patterns, you can write the nth term of that series by writing out the different components that make up the nth term. What I mean by that is this is the sum as n goes from 1 to infinity. We start from the first term and it goes on forever. The numerators of the nth term are always 1. The denominators of the nth term are always the cube root of, well, that's 1 squared, 2 squared, 3 squared, 4 squared. Oh, it's whatever the n is squared. Like that. All right, now, at this point, you might be tempted to say, oh, that's a p series with p equal to 2. Because look, I have an n with a power of 2. I have my n with that power of, in this case, 2. But remember, radicals also count as powers. So you could rewrite this as the sum as n goes from 1 to infinity of 1 over n squared, and then a cube root is the same as a 1/3 power. So that would give you the sum as n goes from 1 to infinity of 1 over n to the 2/3 power. And now this is a p series. The thing about a p series is it must be a constant. And you say, well, it doesn't have to be 1. Well, yes, but given the way a series works, you could always factor a constant out. Remember, these sums are linear. You factor out a constant. So here we have 1, it could be any constant, over n to the p. There shouldn't be plus anything down here. There shouldn't be minus anything down here. There shouldn't be anything here other than n to a power. No roots, nothing else, just n to a power. Once we arrive there, that's how we know we have a p-series. We have n to a power. So here, this is a p-series. And remember, p is just whatever power is on the n. P is just whatever power is on the n. So here, the p is 2/3. Oh, but that's enough. Because now my theorem says that if I have a p-series, it'll converge if p is more than 1, and it'll diverge if p is less than or equal to 1. Oh, but that's what I have here. Since p is equal to 2/3, then that means that p is less than 1. So that must diverge. So does the series converge? No. The series diverges using the p-series test since p is equal to 2/3, which is in fact less than 1. Right? This would be your full answer. Does it converge? No. Here's the test that I used, and here were the results of my test. At this point, we should also make a note that there is a special case of the p-series, which is called the harmonic series. So, I wouldn't really even call this a theorem. Let's just say note. The p-series with p equal to 1, which would look like this. The sum as n goes from 1 to infinity of 1 over n to the 1, or really just 1 over n, which would look like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot dot dot, is called the harmonic series. The name comes from harmonics, as in sounds, acoustics, and it has to do with the overtones of an ideal string in a stringed instrument. The overtones are 1 full length of the ideal string, half the length, a third of the length, a fourth of the length, and so forth. I don't know enough about sound engineering to go beyond that basic explanation on its name, but it does come from acoustics, as in harmonics. Yeah? The p-series is divergent since the harmonic series is a p-series with p equal to 1. Well, then that means it must diverge, which is a little bit strange to some. Notice these numbers go to 0, right? 1, 1/2, 1/3, 1/4. As n approaches infinity, these numbers drop to 0. And yet they're still big enough that they add up to something that's infinite in size. It diverges. But in any event, that is it for the section. Let's see here. For a little bit of extra practice, you should try the following problems. Section 9.3. Go ahead and try problems 3 through 37 odd. I will not, so this is the practice for the section. Although I will not be at all requiring it, along with the exercises of this section, if you go to problems 69 through 79, 69 through 79 are a review of series up to now. These are some problems that are going to cover just a few basic things that we've seen. Well, we haven't seen very much. We've seen the geometric series. We've seen the telescoping series. If you have a geometric series, the geometric series comes with its own test, meaning, oh, is this a geometric series? Yeah. Is r less than 1 in absolute value? Yeah. Well, then you know what happened. Is it greater than 1 in absolute value? Yeah. Okay, then you know what happened. So the geometric series comes with its own test. Likewise with the telescoping series. The telescoping series comes with its own test. The telescoping series test is this a telescoping series? Yes, then it converges. We also have seen the nth term test. We've seen the integral test. And we've seen the p-series test, which really is a special case of the integral test, but it's simpler since you don't have to go through the full integral. And a special case of the p-series test is the harmonic series, right? If p is equal to 1. But here, that's not its own separate test. That really is just, oh, it's a harmonic series. It's a p-series. So we've seen these 5 tests. In the next few sections, we'll be seeing another collection of tests, another 5 or 6, which will be joining these. So right now would be a good time for you to review the ones that you have now so that you get these straight and be able to distinguish, oh yeah, this is the kind of series this is the kind of series this is the kind of series this is, until you have these straight. It may not be the best idea to move forward and add more to this collection, more to this list. All right? So that is it for the section. I hope you all have a nice day. And if you have any questions, please let me know.